Hi, welcome everyone. In this video, we'll discuss about numerical integration. Actually, it is finding the value of a definite integral within the limits by breaking the interval into small subintervals and finding the value of function at each interval. So, we'll go in detail in this video. The topics which are to be covered in this video are a brief introduction, then about quadrature, then Newton-Cotes formula, and from that Newton-Cotes formula we'll derive trapezoidal rule, Simpson 1/3 rule, and Simpson 3/8 rule. The basic problem in numerical integration is to compute an approximate solution to a definite integral to a given degree of accuracy. So this is an example of a definite integral where limit from a to b of fx dx. Now numerical integration is used to calculate a numerical approximation for the value s. So in this figure we have plotted the function in between the limits a and b. So this shaded area, this is s, the area under the curve defined by fx. So bounded by this curve fx within this interval a and b. So this is the numerical integration, or actually the area under the curve. Now the process of evaluating a definite integral from a set of tabulated values of integrand fx is called numerical integration. So in general, numerical integration is the approximation of a definite integration by weighted sum of function values at discretized points within the interval of integration. That is, mathematically, this definite integral fx dx from a to b is approximately equal to sum of value of function at different discrete values of xi multiplied by this weighing factor or weighted factor. So it depends what type of quadrature you are using, this weight function will change. This process, when applied to a function of single variable, is known as quadrature. Okay, so let us move on to the quadrature. Mathematicians of ancient Greece understood that the determination of area of a figure is a process of geometrically constructing a square having the same area, which is known as squaring. Thus, the name quadrature for this process. So they give the name of quadrature. So thus, it is a process of constructing a square with an area equal to that of a circle or any other figure bounded by the curve. So you have to draw a square or rectangle around the figure, and this process is called quadrature. So quadrature rules based on interpolating functions. A large class of quadrature rules can be derived by constructing interpolating functions that are easy to integrate. So first you can make a polynomial for this data points, given data points, and then you can integrate that polynomial and you can easily find the value of integration. Typically these interpolating functions are polynomials because they are easy to integrate. But in practice, since polynomial of very high degree tend to oscillate wildly, so they oscillate at a rapid pace. So only polynomial of low degree are of our interest or used. So typically linear or up to quadratic only. So one such method is midpoint rule or rectangle rule. The simplest method of this type is to let the interpolating function be a constant function, that is a polynomial of 0 degree that passes through the midpoint a plus b by 2 of the interval, and corresponding value of function is f of a plus b by 2. So how it looks, suppose we have this diagram and we have a function given by this red curve. So what is the midpoint rule? You take any point between the subinterval and you have to take midpoint of that interval. So then you have to calculate the value at this midpoint, and these are the constant functions. this one. Okay, so they are polynomial of 0 degree. So in this case, definite integral is approximately equal to b minus a f of a plus b by 2. Obviously, you can increase the accuracy by increasing the subintervals. Then trapezoidal rule, if we consider the quadrature of first degree of polynomial, that is the interpolating function, it will be of straight line, that is polynomial of first degree, passing through the points a and fa, corresponding function value, and b and fb. So if you consider interpolating function to be a straight line passing between the 2 points, then it will lead you to trapezoidal rule. So in this figure, the illustration of trapezoidal rule is shown, and we see that again the red curve is the function, and this squares or rectangles, we have to take the value simultaneously at 2 points, not only at the midpoints. So not only at the midpoints like in midpoint rule, but at the 2 corners, that is A and B. Okay, so you see here the difference. Midpoint has more error at the corners. Okay, they are matching the function only at midpoint, whereas if you interpolate this curve with the polynomial of first degree, that is straight line, so they are matching at 2 points, but the error is now lies where the function is bending. Okay, so since straight line does not have any bend in it, so error is because of that. So in this case, definite integral is given by b minus a multiplied by f of a plus f of b divided by 2. So average of the 2 function values at the point a and b. So this leads to trapezoidal. Similarly, if you take a higher order, then you can lead to Simpson rule. So for either one of these rules, for example midpoint rule and trapezoidal rule, we can make more accurate approximation by breaking up the interval a and b into some n number of subintervals. You keep on decreasing or increasing the number of subintervals, that is, you keep on decreasing the step size, your accuracy will be increasing. So then computing an approximation for each subinterval and then adding up all the results. This is called composite, extended, or iterated rule for midpoint or trapezoidal. Okay, so let us consider, for example, the composite trapezoidal rule, which can be written like this: definite integral is equal to b minus a divided by n, f of a by 2, then plus f of b by 2, and in between we have summation over discretized point, summation of function over discretized points. You can easily derive this formula from the previous slides. So where h is equal to b minus a divided by n, this is step size, and k is 0, 1 up to n minus 1. Okay, so this is the composite trapezoidal. So quadrature is helping you to find the integral. It is to be noted here that we used subintervals of same length. So the step size is same, but one could also use intervals of varying length as well. So what is meant by varying length? Suppose your function is a constant in between certain subinterval, so you can take a bigger step size in that interval, but in certain interval your function is varying drastically, or varying zigzag kind of shape. So in that case you need more points in that subinterval, so you can increase the number of points by decreasing the step size in that subinterval. Okay, so interpolation with polynomial evaluated at equally spaced points in yields the Newton-Cotes formula. Okay, so Newton-Cotes formula, it is a rectangular rule when n is equal to 0, it is trapezoidal rule when n is equal to 1, it is Simpson rule when n is equal to 2. So n is equal to 0 means a constant function, then straight line function n is equal to 1, then quadratic function n is equal to 2, and so on. If the interval between interpolation points can vary, we find another group of quadrature formulas such as Gaussian quadrature formulas. This is in our syllabus, so we'll discuss in next video about this method. So a Gaussian quadrature rule is typically more accurate than Newton-Cotes rule. So let us move on to Newton-Cotes formula first. We derive the formula for Newton-Cotes method. Suppose we have a definite integral denoted by I, limit from a to b, fx dx, where fx takes the value y0, y1, y2, so on up to yn for given x0, x1 up to xn. So y0 is value of function f at x0, okay, and so on. So now let us divide interval a b into n subintervals. Suppose we have this function curve and we divide interval a b into n subintervals, each of width h, so that x0 is a. So first point a is x0 here. The next point is a plus h, which is x0 plus h, then x0 plus 2h, so on up to x0 plus nh, which is the end point of the interval. So it is b. So a b is divided into subintervals, each of width h. Okay. Now on putting x is equal to x0 plus rh, and so we are changing the variable now. So dx becomes h into dr. So the above integral I becomes x0 lower limit, x0 plus nh above limit, upper limit, integral fx dx becomes h, limit from 0 to n, f of x0 plus rh into dr. So we have changed the limit by substituting x is equal to x0 plus rh. Okay. Now on using Newton forwards interpolation formula, we simply putting the value of f of x0 plus rh by using Newton forward interpolation formula. So this is Newton forward interpolation formula, y0 plus r delta y0 plus r into r minus 1 divided by 2 factorial delta square y0, and so on, other higher order terms. Okay. Then simply carrying on the integration term by term, we get this equation where nh is outside the square bracket, and inside we have terms of y0, delta y0, delta square y0, and so on. I have written the terms up to delta 6y0. So 6 other terms I have written. So this is our equation number 1. This formula is known as Newton-Cotes quadrature formula. So this is the general Newton-Cotes quadrature formula. From this general formula, we can deduce the important quadrature rules by taking or by substituting n is equal to 1, 2, 3, so on. Okay. So n is number of intervals or subintervals. Okay. So first is trapezoidal rule. This rule can be deduced from Newton-Cotes formula by putting n is equal to 1 in equation 1, previous equation, and taking the curve through the 2 points x0, y0 and x1, y1, a straight line. That is a polynomial of first order, so that differences of higher order than first becomes 0. So it is if the polynomial is of first order, then the differences of higher order, that is second, third, so on, they will become 0. So we simply get integral x0 from x0 plus h fx dx. Now here you see that n is equal to 1 here, so it means we have considered only one subinterval. So h, the equation reduced to h y0 plus 1 by 2 delta y0. So simply h by 2 y0 plus y1. Similarly, if we take another step size from x0 plus h to x0 plus 2h fx dx, so step by step we are increasing. So this gives you h by 2 y1 plus y2 and so on up to nth interval. So x0 plus n minus 1 h to x0 plus nh fx dx comes out to h by 2. On similar trends, if it is x0 plus h, then y0 plus y1, x0 plus 2h, it is y1 plus y2, and here it is x0 plus nh, so yn minus 1 plus yn. Okay. Now we have to calculate the definite integral from x0 to x0 plus nh. Adding these terms on left hand side and right hand side, we get left hand side becomes integral from x0 to x0 plus nh fx dx simply, and right hand side we have taken h by 2 common, and y0 and yn, these are the terms, we taken them out, and except y0 and yn, the other terms are coming twice in the addition. So 2 times y1, 2 times y2, so on, 2 times yn minus 1. Okay, so this is our trapezoidal rule. Similarly, next method is Simpson 1/3 rule. So this rule can be deduced from Newton-Cotes formula by putting n is equal to 2 in equation 1 and taking the curve through x0, y0, x1, y1 and x2, y2 as parabola, that is polynomial of second order, so that differences of order higher than second becomes 0 on the similar steps as that of trapezoidal rule. So in trapezoidal rule, we need the value of function at 2 points simultaneously, and in Simpson 1/3 rule, since it is of quadratic polynomial, we need, and that is true as parabola, so we need 3 points, value of function at 3 points simultaneously. So x0, first x0, then x0 plus 2h fx dx becomes, by substituting n is equal to 2, so 2h y0 plus delta y0 plus 1 by 6 delta square y0, and on substituting the value of delta y0 and delta square y0 in terms of finite difference, we receive h by 3 outside, and inside y0 plus 4 y1 plus y2. Okay, remember we have 3 points here, x0, x0 plus h and x0 plus 2h, since we have to consider 3 points simultaneously. Then further, from x0 plus 2h to x0 plus 4h fx dx becomes, on similar steps, h by 3, y2 plus 4y3 plus y4, and so on. For nth term, we have h by 3, yn minus 2 plus 4 times yn minus 1 plus yn, and n being even here. So you see here, every time it is a even number. So n is a even number here. Okay. So again, following the similar step, if we add all these equations, left hand side becomes definite integral from x0 to x0 plus nh fx dx, and right hand side we take out h by 3, and we have y0 and yn appearing once, and then y1, y3, so on up to yn minus 1, they are multiplied by 4, plus y2, y4, so on, yn minus 1 and minus 2, they are appearing twice, so they are multiplied by 2. Okay, so this is Newton 1/3 rule. Please note here that for this method, n is even because the given interval has to be divided into even number of subintervals, since we require area of 2 strips at a time. So if you have 3 points, so 3 points have 2 strips. You can make one strip out of this set of points x0, y0 and x1, y1, and second strip of out of these 2 points x1, y1, x2, y2. So this is the reason we kept n is even. Similarly, Simpson 1/3/8 rule. This rule can be deduced from Newton-Cotes formula by putting n is equal to 3 in equation 1 and taking the curve through xi, yi, where I can take value from 0, 1, 2, 3, 4, 1, 2, 3. So it means you have to consider 4 points simultaneously as a polynomial of third order, so that differences of higher order than 3 becomes 0. So simply we get from x0 to x0 plus 3h, and remember we have now 4 points, x0, then x0 plus h, x0 plus 2h, and x0 plus 3h. We have taken 4 points simultaneously in between lower to upper limit, which comes out to be, on substituting the values of these individual deltas and their higher order, 3h by 8, y0 plus 3y1 plus y3y2 plus y3. So these terms, they are coming by substituting n is equal to 3 in equation number 1, that is Newton-Cotes formula. Similarly, for next subinterval, x0 plus 3h from to x0 plus 6h, the value of function from Newton-Cotes formula comes out to be 3h by 8 y3 plus 3y4 plus 3y5 plus y6 and so on. For the last interval, that is from x0 plus n minus 3h to x0 plus nh fx dx comes out to be 3h by 8 yn minus 3 plus 3 yn minus 2 plus 3 yn minus 1 plus yn, where n is being multiple of 3. Why multiple of 3? I have already explained, because you are considering the polynomial of third order. So on adding these integrals, we get left hand side is the definite integral, and on right hand side we have 3h by 8 y0 plus yn plus 3 times y1 y2, then y3 break, there is no y3 here, then y4 y5, y6 is not there, so on up to yn minus 1, and 2 times the terms which are not in second term, that is y3, y6, yn, and so on up to yn minus 3. Okay, so this is Simpson's 3-8 rule. Note that for this method n is a multiple of 3. I've already explained why we need multiple of 3. So alright, so we have derived from Newton-Cotes formula the trapezoidal rule, Simpson 1/3 rule, and Simpson 3/8 rule. So let us consider a numerical of evaluating the integral, definite integral from 0 to 6 dx y 1 plus x square by using these three methods: trapezoidal, Simpson 1/3, and Simpson 3/8. So let us divide the interval, since we are have to apply trapezoidal, Simpson 3/8 simultaneously, so they must satisfy the condition of subinterval for each of this method. 3/8 demands that n should be multiple of 3, and Simpson 1/3 demands it should be even, and a trapezoidal rule you can take any number. So let us divide the interval 0 to 6 into 6 parts, each of it 1, h is equal to 1. So 6 is multiple of 3 as well as it is even. So we can apply Simpson 1/3 and 3/8 rule successfully. Now the value of function fx. So fx is here, it is 1/1 plus x square. It is the values are given as below. So at x from 0 to 6 in the steps of 1, we have y is equal to fx. Value of y0 is by substituting x is equal to 0 here. So 1, 0.1, 0.2, 0.1, then so on up to y6. So we have y0, y1, y2, so on up to y6 from this table. Now by trapezoidal rule, so we have trapezoidal rule h by 2, y0 plus y6, so plus 2 times rest of the term. So it gives on simplification 1.4108. Okay, so this is the value of definite integral using trapezoidal rule. Now we apply Simpson 1/3 rule. So according to Simpson 1/3 rule, it is h by 3 y0 plus y6 plus 4 times y1 y3 y5 odd terms plus 2 times y2 y4. These are even terms. So h is 1, so 1/3, substituting the value of individual y values, we get answer 1.3662. Okay? So from Simpson 1/3 rule, we have the value of definite integral 1.3662, which is different from trapezoidal rule. Now let us apply Simpson 3/8 rule. So here we have the formula 3h by 8 y0 plus y6 plus 3 times y1 y2, then y4 y5, and plus 2 times y3. Remember, we should not consider y6 here because it is already counted in this term. Okay, so if there is y9, then we can consider y6 here and y9 here. Okay, but do not consider the term y6 2 times like in this method. So on substituting the value of h and individual y's, we get value of Simpson 3/8 rule integral of 0 to 6 dx 1 plus x square comes out to be 1.3571. Okay, so we have applied these three methods for finding definite integral of 1 over 1 plus x square from 0 to 6. And obviously, if we calculate the actual integral by solving the actual integration, definite integration, we find that the actual integration comes out to be closer to 1.4 approximately. So it is closer to Simpson 1 by third rule. Okay, so you can increase the accuracy by actually decreasing the step size. As it was clear from the figure that you have to assimilate the function. So if you consider straight line, you don't have bend in between straight line. If you consider quadratic, okay, it has the bend but only one bend. But if your function is varying or changing fastly, then you have to consider higher order polynomial. But generally that is avoidable. You can increase the steps, decrease the step size by for increasing the accuracy. All right. So in this video we have discussed about introduction of numerical integration. Then we have dealt with the quadrature, how to use quadrature for solving integration. Then we have derived Newton-Cotes formula, and then we derived trapezoidal Simpson 1/3 and 3/8 rule from Newton-Cotes formula. So thank you for watching this video.